Hello everyone. As I promised in my previous videos, I'm going to talk about how to collect LTTng traces and load them up in Tracecompass in this video. LTTng is an open source tool developed by Fissuous, which is a front end for tracing kernel and user space events. In this video, I will be only focusing on kernel events, however. So in this website, you can access a very nicely written tutorial on LTTng and how to install it. I will not go through the installation. The installation is relatively straightforward for mainline distributions, including the Ubuntu. Following these steps will install LTTng in your system, and you'll have to follow through the procedure. You'll have to create a tracing group. You have to make LTTng part of that tracing group. You'll have to run a LTTng session daemon, which after reboot, after installation, it's going to be run automatically. But I'm going to basically leave those out and trust that you can easily do that yourself following this tutorial in this web page. Okay. So I have already installed LTTng on my system, and what I'm going to do is I'm going to just type in LTTng list, which will list, when provided with -k, meaning -kernel, it's going to list all the kernel events that are interceptable by LTTng. Now, the list is not as much as you would get from ftrace or perf, but these include the main events. Now, so a question here would be, why use LTTng? Okay, when you have perf, when you have ftrace? Well, there are a few reasons. One of them is that LTTng produces the trace output in a format called compressed trace format, or CTF. Now, CTF is very good in giving you condensed event files, or event logs, if you may, right? Trace files, basically. So that's one reason. It's also very efficient. And the other reason is that LTTng is accompanied by this very nice trace visualization tool called Tracecompass. I have Tracecompass already installed here, so I'm just going to run it. Tracecompass is also developed as an open source tool by Ericsson. It's a Eclipse project, and it's a trace visualizer, right? We'll walk through this once I collect the traces, and I'll show you what the capabilities of Tracecompass is. Although Tracecompass has its own dedicated YouTube channel, and you can refer to that, and the guys there have done a very good job in preparing some nice videos there. So I won't be covering Tracecompass, as this is not going to be a Tracecompass tutorial, but because we're collecting LTTng traces and then we're going to load them up in Tracecompass and visualize it there, then we'll actually go through some interesting features of Tracecompass as well. Anyways, let's go back to the main purpose of this video, which is tracing with LTTng. So some of these events, LTTng list -k, are as follows. For instance, all the events starting with block underline, they are for the disk block device. We have memory compaction events, we have general purpose IO events, we have interrupt related events, IRQ related, for the journaling. We have kernel memory events, malloc, cache alloc, so on and so forth. We have virtual machine, KVM events, and then events for when a module is being loaded or unloaded. We also have networking events. These are all networking events. What else? We have scheduler events, which are very, very useful as the baseline set of events that you always want it to be enabled, because you can know what thread is scheduled on each CPU. So you can get an idea of what's going on in the system. We also have these SKB and SOC events, which are also related to networking. And we have the LTTng state dump events. These are auxiliary LTTng events that provide us with rich set of information about different process values. So for instance, LTTng state dump file descriptor will tell us what every file descriptor actually points to for every given process. So let's say you see a file, you see some process accessing file descriptor 10, but you don't know what this file descriptor 10 refers to. Then LTTng state dump file descriptor event, if enabled, will tell you the list of all file descriptors opened by that process and the actual file that they refer to. We have the network interface, we have the block device, interrupt, process state, so on and so forth. Timer events, memory manager, VM scan, virtual memory scan events, and kernel and work queue events, and all sorts of events. Okay, so these are some of the events that LTTng provides you from the kernel. Okay, so what I'm going to do next is I'm going to be running LTTng tracing sessions. Now I do have a LTTng daemon running, LTTng session D. Just going to grep for this. So you see that this is running, meaning that when I run an LTTng, when I create an LTTng session, my session can actually be created and the events can be intercepted and recorded. Okay, so you got to make sure that this is running. Now, here I have some examples. Let's say the first example to look at is we just want to do the bare minimum, which is usually we want to look at the scheduler events. Scheduler events, schedule switch and schedule waking and wake up. So I specify it as a wildcard, meaning that waking and wake up will both be matched here. I also include the interrupt request events because it's interrupts are also served by the scheduler. Scheduler executes the interrupt service routine, so it makes sense for them to be also included here. We have many different scheduler events. All of these are actually scheduler events, but for the purpose of this example, I only need to know which process is running. So schedule switch and schedule waking and wake up would be sufficient. And this is usually the case most of the time. So in fact, this is where you would start any sort of tracing. Let's say you want to drill out into a problem. First thing you have to do is to know what thread or process was scheduled on which CPU at what point in time, right? That's the bare minimum thing that you want to do. So this is actually the bare minimum tracing that you would always want to try when you want to investigate an issue. So I start with LTTng create. LTTng create creates a session. And here, this is a bash script, so I'm just taking whatever parameter is given as the first argument and passing it to this bash script. This is just going to be some string. So I create this session, then I say enable event. Enable event -k, meaning that these are going to be kernel events, and these will be the events that I want to enable. Then I could say LTTng start, which would start the tracing, and then I'm just going to sleep for 10 seconds, and then LTTng stop is going to stop the tracing. LTTng destroy is going to entirely rip down the tracing session and dump the buffer to the disk. Basically flush the tracing buffer in the RAM to the disk and finalize everything, right? However, there is a mysterious command here, LTTng add context. Now, this is usually what I always put, whether or not I'm tracing LTTng scheduler events. But sometimes when you're tracing scheduler events, you may not need this, right? But I always put it there. And this is to attach a context information to every single event that LTTng records. So anything that you add as a context will be added to all of the events that you are enabling here. So let's say schedule switch, schedule waking, wake up, and all the 5 RAQ events that I'm enabling here, they will all have a context. So what is the context? These are kernel context, meaning that these will be attached to the kernel events. -T means the type. It's a TID context, meaning that the TID that in which this particular event was triggered will be attached to that event as a context. We also have the PID context, meaning that the PID will also be attached, the proc name, the process name, and its priority. So what this does is that for every event that is intercepted and recorded, that event would be accompanied with a context, and that context would include the TID, the PID, the process name, and its priority in which this particular event was triggered as part of that. Okay, so that's how this is going to work. And let's just run this. I'm just going to say LTTng. Now you can just type in the commands, but this is just more convenient for me. Scheduler, and I'm just going to say scheduler sample, right? Or scheduler demo. Okay. So session created, the trace output will be written to this place, and kernel event schedule switch created, this created in channel 0, and then context added, and then tracing started, and then tracing stopped, and session destroyed. So here I'll have my events. So you can see that there's a kernel folder here. If I go like this, I can see that, oh, inside here, actually, I have all of my events. I have 15 different files, actually 16 different files here, channel 0, 0, 0, 1, corresponding to 16 different cores. So for each CPU core that I have, it's going to create a separate buffer and a trace file. Eventually, it's going to dump it to a trace file, right? So this behavior can be changed, and that's more advanced stuff, which you can definitely see in the page that explains LTTng, but I'm not gonna talk about it. We'll just go over the basic default behavior, right? And this is the trace metadata, and that be it. Okay, so we have this, and this is just binary data, right? Now what I want to do is I want to load this up in Tracecompass. I'll go to my Tracecompass. Let me just close these projects. Just close them. And I'm going to create a new project. It's going to be a tracing project. I'm just going to say LTTng Demo and finish. LTTng Demo is created. Now what I'm going to do is I'm going to right click here and then say import. Import a trace import. And I'm going to browse. I'm going to go over where that was. LTTng traces, actually LTTng trace. So, okay. LTTng traces and LTTng demo. Yeah, sorry, scheduler demo. There you go. Scheduler demo, and here in the top folder, I'm just going to say open. Select this guy, right? Selected. and create an experiment automatically with the name. So an experiment is a collection of trace files. So it can contain one or more trace files synced, all time synchronized together. Here I only have one. So, but I intend to always use an experiment and not work with individual trace files. It's just a good habit to have. So finish, experiment, double click, and here it is. Okay, so here we have some basic set of visualizations. Starting from statistics, it gives you some statistics about the pie chart of events that you have collected. So here are the event types. Sketch switch is actually around maybe half of the events that I've collected, a little bit less than half, and all the rest, right? So you have a pie chart here as well, telling you which ones are taking them, are, you know, have the largest count. Sketch switch has the largest count here, right? And then wake up and then waking, okay? And here you actually see the events themselves. So here the trace is from the kernel, and this is the time in nanosecond granularity, and this is the channel, and this is the core, CPU core, okay? And this is the event type, and this is the contents or the arguments of that event. So for instance, sketch switch here is telling me I'm going from swapper 0, which is, this is happening on core 0. I'm going from swapper 0, which is the idle process, with TID 0 to the OBS next process with the TID 17,263 with priority 20. And then here you can see the context, VID, VTID, VPID is 00 because it's running in the context of the idle process and the priority 20, okay? I also have the control flow view, which is a thread view of whatever is happening in the system. So these are the different threads. If I just slide this to the side, you'll see the TID and the PID for those. And so these are the different threads. And if I click here on the legend, you can see the color codes here. Green means a process is running in user mode. Blue means it's in system call or kernel mode. This red is when an interrupt happens, waiting for a CPU, wait blocked for like IO wait, and just wait. Usually this would be idle. You don't have anything to do and you're waiting, okay? That's what it means. So these are the state transitions of the different threads that I have. If I zoom in, I can see that, okay, so for instance, this OBS FFmpeg mux is being scheduled in here, schedule waking. Somebody's waking this up. Somebody is waking this guy up. It's waiting for the CPU for this time. And then here it's given the CPU and it's in user mode, right? So eventually the sketch switch happens. It goes from idle. That core 5 is going from idle to basically running this process, right? And then we have the resources view. The resources view tells you the state of every CPU core. So the control flow view is the thread state, right? The state or the activities from the thread's point of view. This is the core point of view, CPU core point of view, and of course the interrupt line point of view, and the soft IRQ points of view. So because I've intercepted the IRQ events, right, I can get the interrupts as well. So I can see here that IRQ 166, which is this guy, has been triggered. So I'm not sure which one this is, but maybe it's my USB device. I'm not sure. So here, if you see the interrupt handler, I enter the interrupt handler, and then here I'm actually exiting the interrupt handler, and the total time spent in the hardware interrupt handler is 12.5 microseconds down below here as the delta, right? T1, T2, and the delta is here. Okay. So now after that, there is a, well, actually, maybe this is a different interrupt, 166. The tasklet high priority soft IRQ is triggered, and so on and so forth. So you can see everything here. So you can also see that actually on core 4, this thread is running. Then there is an interrupt. If you look at the color coding here, this is an interrupt. Okay, so an interrupt happens here and in the middle, and then this is a soft interrupt happening. Okay, and then again OBS continues execution, right? And then here again another interrupt, the software interrupt, and then OBS continues to function. Okay, so this is the timeline of what happens on the different CPUs. So this is the scheduler events. Now, another nice and interesting view is the CPU usage view. If I double click here, I can actually see a CPU top history over time. So let me just zoom out all the way. So this is the CPU utilization of my system throughout the 10 seconds that I was running the test. And I'm just gonna actually, I'm gonna have these back. Okay, I don't need this one. I need this one, the CPU. Okay, let me just blow this up. Yeah. So these are all the threads. It's not just a history of the CPU utilization, but it's also per thread. And I can select every one of these threads and it will just tell me what's the CPU utilization, or I can just select the entire threads. It's just gonna take a little bit for it to render it, but there you go. You see the different thread utilizations. But if I, let's say, just zoom in a little bit, maybe we can see some interesting things. So here we have a lot of activity on my CPUs. I have 16 cores. So here actually I'm touching, it's almost like full utilization on all of my CPU cores, because this is nearly 1600%, right? Which is 16 cores. Now, if I zoom in, we can see that what are the CPU cores that I'm running, and what is actually taking time on every one of them. So this guy OBS is taking a lot of time. Let me just remove these ones and see what we're left with. Okay. So again, I can remove this one, maybe this one, maybe this one. I'm just trying to get something more appealing to the eye. Maybe look at one of them. Yeah, there you go. So this is, let's say, 2 of these, right? This is how they consume CPU, these 2 threads. So this is also a very nice and useful visualization that you can see. To, let's say you have a CPU hog issue, right? Things are not progressing, things are frozen. You want to know, is the CPU idle? Is it fully utilized? If it's fully utilized, who is utilizing it and why? If it's idle, why is it idle, right? So you can see all of that from this view. So that's the scheduler events. Let's go back now and look at something else. Just going to pull this down. Okay. And yeah, just going to go back to the defaults. Okay. There you go. Okay. Let's go back here. Now, the other experiment that I'm going to run with LTTng is I'm going to look at, so these were scheduler events. Now I'm going to look at system calls. System calls. let's just in LTTng system calls. Okay, this is the LTTng commands that would allow us to look at the system calls. And the only thing different here is that I've actually enabled event for -k kernel dash syscall dash all, meaning I want to see all the system calls. Now, if I didn't want to see all the system calls, it would be as easy as just doing the following: -k dash syscall open, write, read, and close, for instance, right? But in this case, I just want to look at all the system calls. And the reason why you want to look at the system calls, and in particular all of the system calls, is that, let's say you investigate something, right? And then, well, if you don't look at system calls, you don't know if, let's say a thread is blocked, okay? And you want to know why it's blocked. But if you're tracing user space, I mean, if you're not tracing system calls, then you don't know what it's doing inside the kernel. Because when a thread gets blocked, it's because it's waiting on something from the kernel, and it's usually always when there's a system call involved, that the thread is making a system call. That system call is not returning, it's blocking, because either it involves network, it involves disk, or something like that. Okay, so you should know what's going on in that case to be able to understand. You should know the actual system call that's being called to be able to understand why that thread is being blocked. Okay, and you would also want to know what system call is called in general, because um, making system calls into the kernel is relatively costly. It incurs a mode switch between user mode and kernel mode, and then back, right? So you don't want to be calling unnecessary system calls that often. So these are sometimes you have unnecessary printfs, let's say, that would result in a system call. You want to detect that, right? Things like that. So let's run this. So we're gonna say LTTng sys, and then basically demo. Oh, actually, syscall demo. Okay. So now it's going to trace all of the system calls for 10 seconds, and I'm just going to load it up in Tracecompass again. That's it. Okay. Going back to Tracecompass, right click here, import in the same project. I'm just going to import this. It's okay. It's going to be a different experiment. Demo, oh, actually, syscall demo. Okay. Open. Now select this one. You see that the experiment here is going to be like the same name as this one, as the file, and we're just going to say rename. This means that there are trace files with the same name. What do you want to do? Just rename all. And now here we have two experiments, right? Syscall demo. So I'm just going to double click on the syscall demo, and here we have the CPU usage view, we have the control flow view, resources view, and statistics. Okay, so in the statistics, we can actually see that there are a lot of syscalls showing up. Okay. 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 Now, let's go here in the resources view. Let's just zoom in. Okay, something interesting. You see this OBS thread? It's making a lot of these blue ones are system calls, right? Because it says it, right? System call here. So it's telling me that the OBS thread is making a lot of futex system calls. Futex is a fast user space mutex, basically. It's used for handling critical sections between several threads of a process. Okay, so there are a lot of utexes being held here, right? That's what it's saying. Now, some of the times these futexes can block. For instance, let's just go here, and I'm gonna go to the control flow view, and for the OBS. Okay, so I'm just gonna, this is the OBS guy. Well, we actually have a bunch of these. I'm just gonna try to find it. Yeah, there you go. This is the OBS. Why? Because it's at the end of the same futex call, okay? And it's 17256. This is also 17256, okay? Now, look here, futex. This futex is getting blocked because we're getting the CPU from the scheduler is taking the CPU away from this OBS. Because if you look at the legend again, this means wait blocked, right? So this guy now is being blocked, waiting on this futex. It's a lock. It's taking the lock, it's blocking on the lock, and then eventually the lock is released. So this is the time that it's waiting for the lock to be released. If I do the selection here, you see that it's 5.3 microseconds. The negative is because I went the other way around. Like I selected backwards, right? It's just, that's irrelevant really. So this is interesting. If we had not traced these system calls, now we could have traced futex only, but then there are other system calls such as open, read, and write that can block. Had we not traced the system calls, we wouldn't have known why the CPU was taken away from this guy, right? We would have seen everything like green from here to here. Everything would have been green, and then green again here. So why did the CPU, why was the CPU taken away from this? We don't know. Now we have to enable system calls to drill down. So it's usually you start with the scheduler events, and then you go, and then once you need to know why something blocked, you'll need to enable system calls. Or sometimes you just enable them selectively if you have a hunch about what could be the cause of a block process, right? Again, here, if I go at the beginning of this, I can see in the events that there's a syscall entry futex and then a syscall exit futex at the end here, right? On the same, actually not here. Here, I get the scheduler switch, which takes the CPU away from me. But then after I'm given back the CPU here, I finish my futex system call and I exit from it, okay? So this is why you would do the tracing for system calls. Let's see what other system calls we have. Let's look for, let's say, syscall open. Okay, I want to see if we have any open system calls. So it's just searching for it. Probably we don't have it. Nope. So let's see if we have any read syscalls. Oh, actually, I should have said entry open. Okay. There you go. Well, this is open at. What I want is open. Actually, I can do a filter here, pressing this. Let's see if we have open. Well, surprisingly not. So I'm just going to go with a read. Let's say syscall entry read. I could have just said read, and that's it. Yeah. So this is one. Let's just filter on these. Okay, this one. This is a read system call executed on GNOME terminal, right? It's a read on file descriptor 17. Now, I don't know what file descriptor 17 is. So what if I wanted to know? That takes us to the next tracing, which is tracing LTTng state dump events. So in this case, I'm taking all of the system calls. I have the scheduler and interrupt request, and then I'm also adding LTTng state dump that I said it's going to include some interesting information about what a file descriptor actually refers to. Let's just get on with this and run this. experiments. So sys and state dump, Cisco state dump demo. Okay. Now we're gonna trace the system in a different state. It's a different time. We're gonna get a different set of events, but we'll try to illustrate this as best we can. Okay, it's done. Going back to Tracecompass. Again, I'm gonna say, actually here, right click, import, and trace import, and browse where my LTTng traces are, Cisco state dump demo, and then click open. Select this. The experiment is already selected the name here. Okay, done. Rename all, and here is our new experiment. Click here. Okay, we already are familiar with what this means, and I'm just gonna search for Cisco entry read. Actually, here something showed up. It's on file descriptor 80, and it's for pulse audio. Okay, that's the process, pulse audio. The PID, or let's look at the TID. It's 1763. Okay, so remember, file descriptor 80, 1763. So what I'm going to do is I'm going to search for LTTng state dump, and 1763 here. Let's see. Yeah, there you go. This is the those set of information that let's say the metadata, the process metadata information that LTTng collects for that process, which is the pulse audio process. Looking at the state dump file descriptor set of events, we see that for every file descriptor, there's an entry here. For instance, it tells me that file descriptor 7 refers to a pipe, right? These are pipes. This is a socket. This is a file. This is a config file. This is anonymous inode socket. So let's see. File descriptor 80 is, scroll down. If it's something interesting or not. Nah. Actually, this is this is just an event. This is not something interesting here. Yeah, for instance, this other one, file descriptor 75, actually refers to the device sound controller C1, right? And so on and so forth. So you saw that some of these file descriptors refer to actual files, some of them to devices, some of them to sockets, some of them to pipes, and different things. Okay. There are other interesting information that you can get from the state dump events. Let me again go here. You can see the C group information. You can see the so the name of the process. You can see the actually, let me just filter to get rid of the clutter here. Okay, network related. You can see, okay, what else? PID. Yeah, that's the namespace, and those are kind of very deep networking related topics. We don't want to really get into that in this video. Yeah, so there are all sorts of different information here that you can use if you want. For instance, I usually use the file descriptor one to kind of figure out what this is really, that file descriptor is pointing to. Okay, so that is the file descriptor. Actually, that was the LTTng state dump set of events.